All right, this is exciting. This is the first of the four fundamental theorems of vector calculus that we're going to study this quarter. And this is the fundamental theorem of line integrals. And it says that if you have a conservative vector field f, so in other words, f is equal to the gradient of some function phi, then compute the line integral of the vector field f over some path c from the point A to the point B, then that's just the same thing as computing the line integral of the gradient of phi, and this turns out to equal this potential function phi evaluated at the terminal point B minus the potential function phi evaluated at the initial point A. Right, and there's some rather big consequences that follow from this result. So let's go ahead and highlight those. The first is that if your vector field f is conservative, then this line integral is independent of path. Okay, so if I move from A to B along this blue path or this yellow path or this rather crazy green path, all three corresponding line integrals will equal this common value that you see here on the right. So you notice this expression only depends on the values of the potential function phi at the endpoints. It does not care how you get from A to B. Okay, so this is a really big deal from a computational standpoint because if you can find a function phi whose gradient is f, so in other words, if you can find a potential function, then you can completely circumvent having to compute the line integral directly like we were doing in the last section, right, where you have to parameterize the path and then use that parameterization to compute the line integral. Here, all you have to do is evaluate your potential function at the endpoints, subtract, and you are done. Okay, so that is really, really nice. The next comment I want to make here is that this statement looks like the fundamental theorem of calculus, and in fact, it is a generalization of the fundamental theorem that you see in Calc 2. There, you're integrating a single variable function f, and if f is equal to the derivative of some function capital F, right? We call capital F an antiderivative of little f. The fundamental theorem says that this integral is just equal to this antiderivative capital F evaluated at the endpoints, and then again, we're subtracting. Okay, now we're far more limited in terms of the paths that go from A to B. There's just the one oriented path that goes from A to B since we're moving in a one-dimensional space, right? Just the x-axis. The other thing is that the derivative here of capital F, that really is the single variable gradient that you see up here. So this statement for the fundamental theorem really is just the fundamental theorem of line integrals, just in the single variable setting. All right, cool. And now let's go look at the proof of the theorem. And so we'll start here by parameterizing our path C with the parameter, or sorry, using the parameter t. So we'll say that we're at the point capital A when time is little a, and we're at the point capital B when time is little b. And from the chain rule, I can go ahead and compute the derivative of our potential function phi as this expression. This is just from section 13.5. And I can break that expression up as this dot product. And this vector right here is the gradient of phi. And this vector right here is just our velocity vector as we move along our path, right? If I take our vector function r that's describing our path and differentiate component-wise, that's just going to give us r prime. All right, so now this line integral of our vector field f, that's equal to the line integral of the gradient of phi, because f is conservative. And this integrand right here then from our computation above is just simply the derivative of phi with respect to time. And see, now I can apply the fundamental theorem of calculus, and that says that to compute this integral right here, just evaluate your function phi at these two endpoints and see if we're at this location x of b comma y of b, then we're really just at the point capital B. Okay, and likewise for a, and that does it. That's the proof. All right, so in the next video, we'll go ahead and illustrate the fundamental theorem with question number 3. I'll see you there.